Is it? Yeah, fine. Well, I'd like to give you a very warm welcome to this first installment of FProPer, or if you're cheeky, FProPer. The idea of this workshop is to bring together productivity and performance. And when I was mentioning this to a colleague of mine, he said, "Oh, but don't we all do this? Isn't this what ICFP is all about, right? Productivity and performance." And although I agree, obviously I agree, I was a little bit flabbergasted what to reply to this. And I said, well, but there are different levels of performance, and there's a good reason why this is actually a follow-up on the previous workshops that were called FHPC and then FHNP. See, this is why we had to change it. Anyway, so the idea is that we have productivity, yes, and high levels of productivity, and performance, high levels of performance, but not necessarily HPC per se. So we're interested in all kinds of applications. We're trying to broaden the audience. And actually, let me introduce Mike Rainey. He's a co-organizer of this workshop. So any blame to me and any praise to him, please. Then without further ado, I'd like to introduce Dominic Orchard. It's an absolute pleasure of having him here. He has graduated, he has done his PhD in Cambridge, as I learned today, to my surprise, quite a few years ago. Then he has been moving around, mainly nowadays between Kent and Cambridge, as you can already see from his affiliation. And also, if you look at his title, you can see he has done quite a bit of a journey. I always thought that he has a very theoretical background, and I'm sure he has. But he has always seemingly also been tempted by the performance aspects of it. So I'm really glad to have him on this title, From Sea to Comonads to Climate. Take it away.
Great. Well, thank you so much. Absolute pleasure to be here. Thank you for having me. Some people know me for graded modal types and the granular language and things with linearity and taking inverses of types and all these kind of things. This talk is not going to be about that at all. As I said, it's going to be somewhat of a journey thinking about array programming, and I've had a sort of a leitmotif, a kind of a cycle, a brain worm going around in my brain for about 20 years now, and I seem to keep coming back to a particular programming pattern, and so I'm going to be talking about that and my journey through that and sort of the work I've done around that and where that's led me today. So, cycle 0, the origins, going back 20 years, back when I had much shorter hair. I think it's like the inverse, most people have sort of long hair when they're younger and short hair when they're older, but I had really short hair back when I was an undergraduate, and I was obsessed with C and low-level programming and assembly language and hardware design, and I spent all my time thinking about that, and I had lots of arguments with my roommate about how, the only way to get high performance is to write C code and assembly, and that's what you've got to do. And he was doing this thing called Haskell, and I was like, yeah, it's so slow, man. You could write C code instead. So I did change my viewpoint eventually, but I was still really enjoying C at the time, and I did a high performance computing course in my master's in the sort of the final year, and we were given an assignment which was to take this fluid dynamics simulation. So it was a discrete approximation to the Navier-Stokes equations, equations of fluids, and the idea was to take this C code and to parallelize it and make it faster. That was basically the assignment. And so we had learned various things in this course, and one of the ideas was that, okay, we could take this computation, which operates over arrays, and do domain decomposition. So you split it up into smaller parts, and you compute those in parallel, and there's some kind of communication that has to happen between the parts, and this is the way to chunk it up to get some speed up based on data parallelism. But it was using C, and we were generally sort of told, okay, you should keep it in C and use MPI, so use the message passing implementation to send these rows between the different processors. And I enjoyed this course. I thought, that's great. And I said, OK, I'm going to do two-dimensional domain decomposition, where you split it up across multiple dimensions, so you have to kind of communicate with not just people to the left and right, but also top and bottom. And I thought, that'd be really easy. Was that easy? So I started down this road, and I was trying to do this 2D thing in C, and it just kept not working, and the results were just wrong repeatedly and repeatedly. So with 1 day left until the deadline, I sort of gave up and said, OK, right, I'm just going to start again and just do a 1D, one-dimensional domain decomposition. And OK, I got that working in a day and submitted it and passed. But this was an experience that really stuck with me. At the time, actually, I was getting really, really into functional programming, and I did my bachelor's dissertation, and everything was written in Haskell. But I thought, this is going to be easy doing 2D domain decomposition in C, because I'm a really good C programmer, and it turned out to be very hard. And this was a sort of a formative experience in cycle 0. Now, at the heart of computational fluid dynamics is this pattern, this programming pattern known as a stencil computation. So in a stencil computation, you have some array of values. Here I'm going to call it A. And you loop through that array. Okay, forgive the imperative code down here. We're going to have various bits of code, imperative and functional, throughout this talk. You compute some values of a new array, and you do that based on some small neighborhood of elements around at each position. So if I'm going to compute the position at ij in the array B, I do that from A at ij and some small neighborhood around that, and I traverse the entire array to compute this output. So think the Conway's game of life, or blurring an image, various sort of image filters. But this also comes up in lots of numerical simulation, scientific computing kind of contexts as well. And that's at the heart of these computational fluid dynamics simulations, is a load of stencil computations. And so, OK, if this talk is about my journey, I'm going to fold space-time for the moment and go to the sort of the end part about climate, because fluid dynamics is really important for Earth system models and climate models. The atmosphere is a fluid, the oceans are fluid. That the core of climate models are fluid dynamics simulations. So in this diagram here, it's a kind of like a process model diagram. You've got this bit that says advection up here in the atmosphere and advection down here in the ocean. Advection is the bulk movement of fluids. And the way the core of the climate models is to solve some equations of state for the atmosphere. Conservation of momentum, mass of viscous fluids is basically the Navier-Stokes equations, and that's at the core of our climate models. So inside of all of these is these kind of models is a lot of stencil computations then to compute the movement of fluids in the atmosphere and the ocean. So we'll come back to that, but at the time I didn't really think very much about that in cycle 0, but this lesson was lodged in my brain. And of course, you have to then do this over three dimensions on some kind of grid representing the whole Earth. So let me just show you bits of that code. Has kind of, hopefully you can identify there's the sort of stencil computation things in there like this. This is computing some the pressure equation, and okay, updating velocity. It's getting a little bit funkier, this code. And then you get these really kind of complex kernels which just have lots and lots of array indexing terms in them. And then, oh, look, there's another one that looks almost identical, but is actually different. And they're quite sort of detailed bits of code, really, in these fluid dynamic simulations. So, you get the hang of it eventually, but writing this from scratch at the beginning is a little bit tricky to get right. Just a little plus or minus or an I and a J and a 1 in the wrong place or the wrong variable can make everything go wrong. So we'll come back to that, though, in a future cycle. So cycle 1, DSLs for stencils. This was now fast-forwarding a bit to my PhD, lots of late nights and pizza, and I had sort of moved on from those kind of things, or so I thought, until I was sitting in a seminar one day. I think it was in the first year of my PhD, and I think it was not in the, I can't remember where it was, somewhere in Cambridge, but it was someone who was from a scientific computing background. And they were talking a lot about the optimizations they had done to their code to make it a little bit faster, and it was lots of really clever stuff. It was lots and lots and lots and lots and lots of hard work, and oh, we got a little bit of speed up. And I'm sitting there in the audience thinking, is this right? Okay, I wasn't exactly thinking we need more lambda, but I was thinking, surely there's something that computer science can bring to this, that programming languages can bring to this, and functional programming. We should surely be able to build some kind of functional programming languages or DSLs for scientists that helps them be really productive, not spend all of their time sort of optimizing low-level C code or Fortran code, but that lets them just express the intent of their equations, intent of their solution, and then have it produce really fast simulations that you can retarget. Surely that should be possible. Why don't I have a bit of a think about that? And so I started writing down what I saw of all the kind of problems that I saw in these kind of approaches in scientific computing. Manual parallelization, it's difficult to express, it's error-prone, it's hard to debug. I had a week of not sleeping and eating lots of Doritos trying to do that. Imperative programming languages have a high potential for producing incorrect parallel programs. That was sort of what I deeply felt from my experience. Then often what you end up with is really hardware specific. You've really tailored it to the particular hardware architecture that you're going to sort of deploy it on. And then, okay, maybe there are some automatic parallelization techniques, but in principle they're undecidable, and then they can be really unpredictable. Like maybe your code's really fast one day, you change a little thing, and then it's really slow, and you don't know why. And I was sort of getting this impression that all of these indexing operations were kind of, in the C code, it was very general. You could kind of write anything in the indexing operations, and actually, if only we could just sort of corral things down into a very fixed kind of patterns, which is what I could observe in the sort of code that was around, then we could sort of cut out some of the noise and make the analysis or make the DSL much more fixed onto the problem. So these issues I actually took from a paper that we wrote after I had done some thinking about this, and this in sort of somewhere towards the sort of middle of my PhD, we published this paper about our DSL for doing productive and performant stencil computations. It's called Hypnos, which is a sort of rendering of the Greek word for sleep. You can ask me about why it's called that later. But the idea was to try to solve these issues and have a DSL that kind of dealt with these things. And there were kind of two key innovations that I'll talk about. One was using comonads, having a comonadic interface for arrays, and I will explain what that means. And also having a sort of special syntax and special way of accessing arrays, not just these I+1, J-1 kind of indexing operations, but something that's really quite novel, I think, and abstract, that's sort of decidable to analyze. So at the core of the DSL was the concept of a grid, and a grid is an array paired with a cursor, which is like an index into the array at some point. We sort of had this multi-dimensional grid type, which contains this cursor. Now, I had been getting really into some category theory things, and I'd been thinking a lot about data flow programming and comonads, and I sort of realized, there's this pattern here, and it's exactly the shape of this comonad thing that I've been playing around with in other areas. So a comonad is, it's a data structure which has some operations, and those operations need to have some laws. If you know monads, think you're going to be sort of flipping the direction of arrows. If you don't know monads, well, don't worry about it. Hopefully, you can just sort of follow along with what I'm describing. So the data structure here is going to be this grid thing. It's an array paired with this cursor, as I've said. So the array is indexed by some type A. It contains things of type A. Indexed by I contains A's. And a comonad has an operation, which is called the extract or co-unit operation, which says I can go from a grid A to an A. And how do we do that? Well, the laws force you, there's some associated laws which I won't go into, but they force you to, in this particular instance, to index the array at that particular position. So you're sort of extracting the element that's at the cursor. Okay? And then you have this operation called co-multiplication, which I write as delta, which has to be as follows. You take a grid, and then you produce a grid of grids. Now, these grids, these internal ones, are sort of localized at the position in which they reside. So if you look at this one in the top left, you can see its cursor now is also in the top left. And if we look at the one to the right of it, its cursor is one along, and so on. So it's sort of copies of this grid where the cursor has been moved to every single position. And then that's represented itself as the entire grid with your original position highlighted. So this is a sort of like expand the context into all global contexts, and we'll see why that's useful for stencils in a second. So these grids, they're also functorial. That means that we can take a function from A to B and lift it to a grid of A's to a grid of B's. This is the sort of fmap operation in Haskell. And this is, point-wise transformations on a data structure. It's something we want to do lots and lots and lots of times. But stencil computations are more general than this, because we don't want to just take in a single element A. We want to take in a whole neighborhood of elements that are around the cursor. We want to get that like local neighborhood. You want to compute how fluids move based on the neighbors around it, for example. And that's what's provided by this structure. So the co-bind operation, this is sort of using the Joule's terminology for monads, but the co-bind operation gives you something that looks a bit like fmap, but instead of an A to a B, you're taking a grid of A to B. So you can see this function here, f, as something that's sort of localized at some position, a grid of A's, and from that you're going to compute a B. So this is like a description of the computation at some position. It's the local computation. You're going to run f, and you're located at some cursor, and you're going to look at some neighbors around you and compute a B. And what cobind does is it lifts this local computation to a global computation. It runs the whole thing over every position in your array and reassembles this new array at the end, which is your array of results. So the cobind is taking something local and applying it globally and doing this traversal. And this cobind is derived from that delta, that co-multiplication I had on the previous slide. So what's the derivation? You've got this f, it goes grid A to B. What you do first is you start with the grid A and you do your delta, which then sort of copies that array and localizes it, and then you apply f to every single position, so you sort of map over it, apply f at every position, so you're applying it to every localized point, and then you're assembling that into the output grid. And okay, you don't have to derive it in this way. It's actually more efficient to just write the cobind operation directly yourself, and that's how it works inside of our DSL. But this is the core of the stencil computation pattern. You have this local computation, and then you apply it at every position to compute the new global result. So that was a kind of discovery we had during this project, and it became the sort of the core backbone of the Hypnos DSL, that you write stencil computations, and then you have these combinators based on the comonad and some other things that plug them together, and inside this cobind is where all the interesting action happens with parallelization, because the cobind operation then, if we go back a bit and we can just look at its signature on its own, that's the place where you're traversing the array, and that's where you can then do the domain decomposition. You can have particular hardware implementations and split it up and actually get the parallelization. So the idea was to follow this kind of long tradition of skeletons, parallel programming skeletons, and have these combinators which do the work for you, abstract it, and you just have to write your little local computation. So that was sort of innovation one in the design of the DSL. Innovation two was to deal with these pesky indexing things. And me and my colleague Max Bolingbroke, we had many late nights in our office and just sort of talking about things. And we hit on this idea, which was kind of crazy, but sort of made a lot of sense, which was to use pattern matching to deal with indexing and actually throw out the concept of indexing altogether. So we have this thing called a grid pattern. This is code in Hypnos. It's a pattern match on the left-hand side, and what you're pattern matching on is a grid. But this thing here is a grid pattern between the pipes, and it has this at symbol C, and when you're pattern matching on a grid, what this does is it applies that co-unit operation of the comonad. It extracts the position at the cursor. So C gets bound to the element pointed to by the cursor in that grid. So it's like doing C is equal to AI, where I is your current position in the array. And then if you write a pattern to the left of that, it binds that left of the cursor, and if you write a pattern to the right of that, it binds that to the right of the cursor. So it's like saying L is A index at I minus 1, and C is at I, and R is at I plus 1. And we thought, oh, this is cute. Of course, there are 2 dimensions in text files, so let's make a 2-dimensional version. Oh, sorry, that's in a moment. Okay, getting ahead of myself. Let's just actually write, okay, this is the Hypnos code for taking a grid in dimension X. This B is to do with boundary information, which I'll mention at the end. But okay, this is just a simple kernel that takes those neighbors and averages them. And so I can take my run combinator in Hypnos. This is the cobind, and it applies it onto that grid. Now, there's a little bit of stuff around here. This B is to do with the boundaries, and this particular version deletes the boundaries. So if you want to just iterate inside the interior of an array, and if you're going to change the type, so everything in the array starts off as type X, but you're only processing in the interior and converting things to Y, well, now you have to throw away the boundary because it has the wrong type. But then there's a version of it called run A, where everything has the same type, and this can deal with its boundary, and we can preserve the boundary at the end. So there's some kind of, some subtleties to do with boundaries, which I'm not going to talk about today, but we had a lot of fun working that out. Okay, so the key thing is you write your stencil, like F here, and then you use the run combinator to apply it. So that's 1 dimension, but of course there are 2 dimensions in our files. So we can have a 2-dimensional pattern match as well. So this is the sort of Laplace, is this Laplace? Yeah, the 2-dimensional discrete Laplace operator. And we've got this grid pattern that's now in 2 dimensions. So if we go 1 line above the cursor, then that's going up. That's sort of -1 in the Y dimension here, and the B is +1 in the Y dimension. And so based on the lexical layout of the grid pattern, that's determining how you index the array. And the key thing here is that the shape of the patterns is completely decidable. It's very easy to statically determine then the shape of your access. There's no general expression to analyze. The programmer isn't tempted to do some kind of something more complicated. It's just captured there in this very abstract form using these grid patterns. And that was the sort of key idea we had there for making things very decidable and predictable, so that there wasn't any surprises. Now, there's other things that you want to do then to get increased performance. So one of the particular kind of grids that we had is a double buffering kind of grid setup. So this is when you read from one array and then you write to another, and then after you're done with that, you swap them around. And this can be captured by a comonad as well. So you have a pair of a read array, and I've called this I array for sort of immutable array, and then a writable array, an M array, a mutable array, and then a cursor. So you've got this pair of arrays. And again, the cobind operation is going to give us access to read from the I array here, but it's going to write its results into the M array and then freeze the M array at the end and thaw the I array and swap them around. So kind of swap the role of the immutable and mutable inside after one of these cobind operations. So we had a whole bunch of other kind of crazy stuff in Hypnos as well, where you could pattern match in time, and you could talk about the temporal dimension, and again, that was static, so it would know how many I arrays to allocate. So if you were looking 2 time steps back, then it would say, okay, what you need is 2 I arrays and 1 M array, and that was all statically determined because we reused our grid patterns to match in a special dimension T. So you could do these windows back in time as well, and then it would give you the right comonad. So the general idea, though, was that we wanted to sort of hide these kind of optimizations all inside of our comonadic interface, hide them behind that wall so that you don't have to mess around with doing mutation and things yourself. And then we did have ideas about like all of these really cool optimizations that exist, like stencil tiling and space-filling curves and all this kind of stuff, but we never got to that because I got distracted into co-effects and graded modal things, and then, the cycle died out. But I think there was a lot of cool stuff that we could have done there, actually taking it and making it really even higher performance. As it was, the sort of performance gains were a bit more modest in the sort of 5 to 10% kind of improvements. So we implemented this atop Haskell, and there was a lot of cool stuff trying to figure out how to do that as well. So there was a little bit of syntactic, the patterns got desugared into these indexing operations, and we had this way of leveraging the type system in Haskell to talk about safe indexing. So I'll use the cursor here. So a lot of stuff you have to deal with is the boundaries and making sure you don't get out of bounds access. That's another kind of bug that you can have when you're writing this kind of code. So we had a whole system for expressing boundaries. That's this information B. And then when you're indexing at I, you generate this predicate that I has to be safe with respect to B, so you're sort of not going out of bounds. But all of this is handled automatically by Hypnos because the grid pattern tells you the size of your kernel, so it tells you how big your boundary needs to be. If your stencil looks one to the left and one to the right, okay, then you need a boundary of size 1 on the left-hand side and a boundary of size 1 on the right-hand side. So then when you're constructing this thing, you have to provide that boundary information. It's sort of all handled automatically, and then it's desugared in Haskell into these indexing operations, which use some sort of lightweight dependent typing, and this predicate checks the safety, and we sort of proved that was all sound. So you get this sort of, if you look at the sort of the Haskell code, you get these sort of predicates stacking up and saying, okay, for this little kernel, this little stencil, where you're looking positive 1, positive SZ, so that's positive 1 in one direction and negative 1 in another, and positive 0, then those need to be safe with respect to the boundary. And that, in this function, the boundary is polymorphic. So for any boundary, as long as it has enough to not cause some kind of out of bounds errors when you run this. And as I said, we did do some kind of performance benchmarking, not as much as I would have liked. As I said, I sort of got distracted into the more category theory stuff in the rest of my PhD. But there was some sort of nice ideas there, and okay, I worked on it for a bit, and then the cycle sort of died out for a little while. Now, again, I'm going to go nonlinear, nonlinear dynamics and nonlinear storytelling. So I actually came back to the Comonads for stencil computations kind of later, because I had been thinking about the fact that there's these laws that you have in a comonad. They kind of look a bit like rewrite rules. You can turn them into rewrite rules, and they correspond to some kind of optimizations that you can do to your code. So I think one of the things that I often think about category theory and using it in programming, it's, okay, there's a bunch of sort of useful design patterns here, but also the laws not only tell you what to do, and you can sort of generate tests from them or do proofs with them, but often some of the laws kind of encode optimizations as well. And I wanted to sort of understand exactly how that was true and actually really formalize that. So I did some work, which is really not well known at all, where I looked at these kind of container functors and comonads. So with the stencil computations as comonads, you could then think about doing other data structures like graphs or trees or things like that, as well as arrays, and you can sort of generally categorize these as container functors and container comonads. And I looked at generalizing sort of well-known kind of optimizations and how they come out from the categorical laws. So if we looked at this code on the left here, we'd say, okay, this is a silly piece of code. We've got this sort of inner loop that we kind of repeat because of the outer loop, and so we get some n squared thing going on here with the kernel f, plus then the outside of g, and of course you can just pull this out and go from a quadratic to a linear. Turns out that this corresponds exactly to one of the Comonad laws about embedding in associativity. So I won't say more about it, but this paper sort of really looked at that categorical side and showed that some of these laws corresponded to asymptotic improvements in your code. And so in Hypnos, we turn these into rewrite rules for Haskell to sort of say, look, if someone's written things in a silly way, you should really sort of optimize them using these laws. And finally, sort of years later, I did the work to show that those were not going to make things asymptotically worse, that actually they were potentially optimizations. But I don't want to say more about that. I want to go into the next cycle. So I went and did a whole bunch of other stuff, but this kind of array programming and stencil computations was, again, lodged in my brain. And I finished my PhD, and I there was an academic at Cambridge who I'd spent lots of time chatting with, and he had been sitting down in college and talking to various scientists. And the way that it works in Cambridge and Oxford as well is that you have these colleges where you've got people from all disciplines sort of situated at this place where you kind of go and eat lunch, and students live, and the general thing is that you go to lunch and you sit down next to the next person at the table. You don't go and sit with your friends. You just find the next spot on the table and you sit down and you turn to the person next to you and you say, oh, you know, how's your day going? What are you working on today? You know, and then you have a conversation. He was having these conversations with the other fellows at his college who were saying, oh, you know, I'm working on these kind of plant, these biosphere models, but I can't get it right, and I think there's bugs in my code. And he was like, oh, bugs in your code, you know, well, maybe we can help with that, and maybe we should have some conversations. And he came to me and said, oh, I'm having all these interesting conversations with scientists, and you know, they're having problems writing code, and they're interested about whether computer scientists could help them write better code. And I was like, well, yeah, I think we should be able to do that, right? So we started having these conversations with the scientists, and about, you know, correctness, and I'm going to move around a bit, and we said, oh, well, in computer science, there's been all this work on programming languages, been all this work on verification. There's all these like amazing results of like verified pieces of software. Would you like some of that? And they're like, oh yeah, that sounds really great. And we said, okay, cool, right. So there's this thing, this theorem prover, and you need to know about first-order logic and dependent types. And what? We don't know anything about that. Oh, okay, so what do we do then? So we're thinking, we've got all these great results in PL and verification. How could we possibly get some of these things into the hands of scientists? So we started a project trying to do this, trying to bridge the gap. And we thought, well, let's actually look at what you're doing. Let's sit in a bunch of your meetings. Let's look at your code. Let's talk about it and see how you develop things. And okay, you use Fortran. Didn't think about that so much at the time, but maybe we should start building some tools for Fortran then. And I was going back to then thinking about, I was seeing code that was like this again. I was like, oh no, it's these really complicated fluid dynamics things that I really struggled with. This is C code, sorry, I should switch to the Fortran, but I have a Fortran version of this as well. And yeah, this stuff's really difficult. How do you get this right the first time that you write it? You know, I had first-hand experience of getting this wrong, very wrong. Lots of times. So we started thinking about array programming again and this stencil sort of pattern. And I have been saying like, oh yeah, stencil computation is really important for science. I think it's really important for science. So we sat down a bit and said, okay, let's actually get some evidence for that. So we did a bit of a kind of a study on code. So we took a bunch of packages. They ended up all being climate science related, really. The UM is the UK Met Office Unified Model. It's an amazing piece of software. It's a climate and a weather model used all around the world for both climate predictions and weather predictions. E3ME is a kind of mixed climate econometrics model. Hybrid 4 is a land surface model, which is then used in other kind of climate scenarios. GeosChem is a general atmospheric chemistry model. There's the old Navia code, the fluids, some libraries, and some stuff that went into more like geodynamics and things. So we sort of took these and said, let's build a static analysis that looks at how arrays are used in this code. It's about 2.5 million lines of Fortran code here, and we built a lot of tools for analyzing Fortran. And I sort of had this idea of, well, if we could, first let's get some evidence that this is a sort of common pattern. Which I think it is, and then if it really is, and I think that there are always these kind of very regular things. Okay, we switch to Fortran now. I think there are always this very regular shape, and that was one of like my assumptions in Hypnos. That was like one of the things I was positing, like, oh yeah, stencil computation is always really regular. That's why we can do grid patterns. Instead of having a grid pattern, there should be some sort of like very abstract way of describing this shape. So I was thinking, okay, you know, here. It's really, you're just describing a little rectangle, and it's a sort of a centered thing, it's symmetrical, and it has depth 1, and it's in 1 dimension. So I wanted to design some sort of specification language, which in some ways was really like the Hypnos idea of just using the regularity, but writing a specification that's not like the code. You know, if you write a specification that's the same as the code, well, you'll just get the specification wrong as well, right? So I wanted a specification that was radically different to what you write, but then that captured the same information. So, okay, I think my slides are in a slightly wrong order. We did the analysis. There were tons of stencil computations everywhere. Like 50% of the array computations were stencil computations with a really regular shape, and it was a huge amount of the code base. Okay, so we started designing this specification language. So this centered description, as I said, it captures this kind of pattern of -1, +1, again, going back to this idea. Sometimes you have these kind of biased stencils, and it comes from doing the numerical analysis approaches. And in numerical analysis, you call this a forward approach. So I call this forward to a depth of 1. You're not looking at -1, you're just doing I and I+1, and then there's backward, going the other way. And then sometimes you're just looking at the single one. This is like the super simple case, so we call that pointed. You're just looking at that single point, back to the kind of co-unit of the comonad. And then, of course, depth of 2. And we also noticed that sometimes you get this sort of non-pointed version, where you have that part, but you're not looking at your current value as well. So we saw that as well. So, okay, well, let's put that in as a sort of modifier on these specifications. Now, that's 1 dimension. So you've got this sort of 1-dimensional descriptors, but you also want to combine these together. So we have these region combinators, combiners, multiply, and plus. So what do? So let's say I have a centered dimension 1, depth 1 description like this, so it's kind of capturing this kind of pattern. You can then multiply it by another specification in dimension 2, and it takes the sort of Cartesian product of those 2 specifications. So it gives you this box of 9 elements like this. So it corresponds to code that might be like this, kind of capturing all of those indices inside. Okay, and what do you do with plus? Plus is just sort of unioning the 2 things together, sort of overlaying them. So to get the classic 5-point stencil, you first describe a centered in 1 dimension that's pointed in the other. That's going to give you something like that. Plus centered and pointed in that dimension, and that describes the classic 5-point stencil, which is at the core of Conway's Game of Life and lots of other kind of bits of code. So this kind of scary, we're on the Fortran version now, great. This kind of fiddly, complicated looking thing is captured by these 2 specifications. So we see that U has the 5-point stencil, and V has this kind of forward-backward thing. So it's like a little box, 2 by 2, oriented non-symmetrically, and then the other loop does something which kind of gives us the other side. So I thought, okay, that's great. That's a nice sort of simple specification that you can start with, and then you can write this, and it's going to capture potentially capture some of those bugs. So the tricky thing is, how do you evaluate these kind of approaches? I mean, we had generated a load of evidence that these were common patterns. And okay, here's the thing, I think, so we could run our tool in both a checking mode and an inference mode. So given a specification and some code, you could say, does the code correspond to the spec? You could also give it some code and say, infer the specification. So within our 2.5 million line corpus, there were essentially this number of specifications that we could generate. 73,000 of them were stencil ones. Access is for patterns that are not quite like stencils, but they're things like reductions over arrays. So we captured some other things as well. A lot of them were just really trivial, like point-wise transformations. So the specification was just pointed. A small proportion were just single actions, so also quite simple, and some of those were non-pointed. And then there was a little group of really quite complicated ones involving lots of actions, and then some of them were kind of a little bit more fiddly, and we had to use these approximation operations, which I didn't mention, at most and at least, because there was sort of, actually it's usually just at most that we use, but there was something that didn't fit one of these pluses or multiplies, something a little bit irregular. But our kind of argument was like, okay, this is quite a small percentage, but that's still a lot of code that covers, and these tend to be the really, really critical bits of dynamical cores, really kind of critical solving some PDEs in a discrete way, and they're the really fiddly bits. So if we could have some way to help the scientists write those, then that would be good, and it would be worthwhile. So we thought about how to evaluate this in terms of like catching bugs, because you write a paper about this and then the reviewers say, but have you caught any bugs? We go, well, no, not really, because we don't know exactly what the code is supposed to do, and it takes a long time to sift through 1 million lines of code with some people and say, is this the right specification? Is this the right specification? So I think it was our postdoc, Matt Danish, who had this really good idea. We had access to the version control system for the Met Office, and we said, okay, his idea was to go through the commit history and run our inference mode on the code and look for any places that the specification for a particular piece of code changed between commits, and then filter that by commit messages that had words like bug or fix or something like that. And so we found various examples of places where, yeah, people were saying, oh, there's a bug in this array transformation, and it should be I+1 instead of I. So we saw that because of the change of specification. And sometimes there was one that was a bit like this, where somehow the J and the I were the wrong way around, probably because someone had been trying to optimize it, because Fortran is column major and C is row major, and often people writing Fortran code get it the slow way around. And actually we have a tool that warns you about that as well. But we saw that there was some evidence that, okay, if you had some kind of way of thinking declaratively first about what the specification is, then maybe that would have helped you. Maybe that would have helped you write the code right the first time. That was at least our suggestion. And I thought this was a neat idea, though, kind of going back over the commit history and using the inference to like look for these places where it could have helped. So this project, we developed this idea, but there was, and we published it in this OOPSLA paper, and it had lots of things about how we analyzed the corpus. We designed this declarative shape specification language. It has lots of like neat equational theory things, and it has a denotational model. That's how we do all the actual analysis. We kind of turn things into some sort of denotational representation, which lets us do equality on these things. And then we have checking and inference algorithms, and we applied that back to our corpus data. But we built all of that into a tool which was called CamFort, which does lots of other things as well. So we sort of built a whole Fortran and static analysis pipeline so that we could then sort of start building these verification tools on top and bring in other ideas. And another thing that came out from this time, so slightly away from array computations now, was sitting down with the postdocs and looking at the code. And I was looking at the comments and saying, oh, this is nice. You've got units of measure information in these comments that tells you about what these arrays and what these values are. And then one of the postdocs said, oh, yeah, but that one's wrong. We said, this guy, Andrew Kennedy, did all this work about how units of measure is a kind of type system, and maybe we could build a type system for you. So we built that in CamFort as well. We built this sort of external optional units of measure typing system for Fortran. So now again, a little bit more Fortran here. This is really simple calculation. These bits in green are comments, and in Fortran you use the bang for a comment, but bang equals is the sort of telling CamFort, this is a specification that you need to parse. It has some semantic meaning. So here we're saying the mass is kilograms, the height is meters, and then potential energy is this thing. And notice that we didn't have to annotate gravity because that can be inferred from all of the rest of this information. And so you can give this to CamFort and say, check that this is consistent, and it says, yes, that's fine. You can ask it to infer things for you. You can ask it to synthesize specifications into the code for you, so you can sort of annotate some things yourself. and then click the, run synthesize mode, and it infers everything it can, and then inserts all those comments for you in the rest of the declarations. It has polymorphism as well, so you can describe polymorphic specifications, and it also has this mode called suggest, which I really love, which is you start with a file with no annotations, it looks at all of the constraints, and it says what's a minimal set of variables which, if you annotate them, we can solve all the other equations. And so then you go and add those declarations, and everything else works out. So we were sort of super happy with that, and we showed it to various people, and we showed it to the Met Office, and they were like, oh, that's nice. But really what we're interested in is checking a bunch of other things about our code. So we had a nice project with them, where they had a lot of internal documents about things that you should and shouldn't do in your Fortran code, and we basically codified a lot of those into sort of static analyses. So that was really interesting. We're still working on this project. Bloomberg have worked with us on this as well. They've been using our analysis pipeline too, and we've been able to work together on that. So that project had a lot of different I don't know, axons or like kind of tendrils going out of it of different things that we could do, and we're still trying to leverage that to this day with scientists, which I'll come to in a moment. I just thought this was a good opportunity, though. I know this is a functional programming workshop, and I've pretty much shown you I've shown you a mix of functional and imperative code, but I just want to point something out about Fortran. The little double colon here, so, you know, there's this kind of, nice overlap between Haskell and Fortran in using the double colon for typing, which I noticed after a few years. And people are always a bit confused when they meet me and I'm talking about Fortran. I thought you were a functional programmer. But yeah, that's something funny I noticed. So around this time, we thought a lot about, like, how do we do this kind of research going forwards? What's going to be useful? We wrote, Andy Rice and I wrote this position paper saying, you know, basically we need to engage more with scientists. You know, we kind of, in the early days, computer science in its infancy was kind of like a service to science. The computers that universities had were like these things that were helping the scientists, and there was a lot of interaction. And then, okay, naturally computer science developed as its own field, and it kind of pulled in lots of other things, but we sort of lost that interaction with the scientists. I mean, it's still there somewhat, and you know, people do that, and there's things in high-performance computing, but it's not the same as it used to be, and we should really sort of talk to them more. Perhaps we could design new systems for abstraction and specification. They're a bit more targeted towards what scientists need, so it's going back to kind of ideas like I'd been having in Hypnos and the things that we did in Camfort. And then if we can provide some tools now that help people immediately, maybe we can have a sort of evolutionary approach where future languages can be designed that sort of pull in some of these ideas from the beginning. Okay, it's really hard to make a new language, and you can't just sort of make a new language and say to people, use this language. It doesn't really work. I mean, occasionally it does, but it's very hard to sort of start a new language. But maybe if we have this evolutionary approach, we build some tools now that fit into the existing pipelines, we sort of gradually move towards some better tools for scientists. So we sort of had this paper where we kind of really set out some of the difficulties and then threw loads of like random ideas into the end of the paper of things we could do. So that was cycle 2. Then I went and did a bunch of other stuff like granular and graded types, but you know, it was still lodged in my brain, and I had kind of started down this journey of working with scientists and was sort of feeling like this is really what I'd like to keep doing. I tried to get various bits of funding to have other projects with scientists, and that didn't work for several years until finally we did have this sort of big score in terms of funding, and we're able to set something up, which I'll talk about now. I mean, for a long time, really, I'd been thinking about these problems as well. So if you haven't seen this before, this is a wonderful graphic by Ed Hawkins at the University of Reading, which visualizes the global mean temperature, the change in the global mean temperature over the last 170 years. So the color coding corresponds to change in temperature over an average baseline in this data. We all know that things are getting hotter and rapidly hotter, and we also know that this correlates with a very steep uptick in the atmospheric concentrations of CO2, which haven't been there for a long time, and then we've suddenly, due to our activities, have had caused this massive spike. And you could look at these two graphs and say, okay, it's a correlation, is it causal? But there's been all this amazing modeling work for a long time, and I love this graphic because it embeds so much of sort of human knowledge and human activity. This is from the IPCC, last IPCC report. There's this sort of observed line, so this is time on the x-axis, temperature on the y-axis. The black line here is the observed mean global temperature, and we see that going up along here. And then this kind of brown line in the middle is the aggregate average of all of these simulations of huge amounts of modeling work across lots of different groups, lots of different models, kind of aggregated all together, simulating the world's atmosphere, but including all of the sort of human factors, what we call forcings, inputs into the system from human activities, as well as the natural ones as well, volcanoes and geothermal heating and things like that. And we see that that tracks very closely. Okay, there's this sort of error margin, this level of uncertainty around here. But then if you do the same simulations and you take out the forcings from the human activities, well, then things just stay along here and you get basically not much warming at all. So this gives us sort of very kind of strong indicator that the warming that we're seeing isn't just some natural cycles. It's something that's being caused by our activities. And there's huge amounts of really deeply interesting computation that goes into these kind of graphs. Now, another thing then you can do with models is predict out into the future and sort of do these what called scenario testing. And so there are a bunch of, in IPCC land, there's these things called shared socioeconomic pathways, SSPs, where you sort of look at different scenarios that might go going forwards. So net zero by 2050 is this blue one here, and this prediction says, well, if we do that, then our warming will go a bit above 1.5 and then slowly kind of go down towards the end of the century. Dark blue is, we make a really good effort by 2050 and then sort of maybe hit net zero later on in this century, and we go up somewhere about 1.75, and then, these are kind of progressively bad situations where we basically sort of business as usual. 2050, we kind of get really terrified, and then we make net zero by 2100, but that's already pushing up close to 3. Late Cretaceous period, where we've got palm trees at the poles, is somewhere around this region. So that's not a great place that we want to be. So what, as a programming languages person, could I do about this? Well, maybe I should try and help with the climate modeling. At least that's something I could do, and that's something I was thinking about for a long time. And I read this wonderful book which kind of captured it, one of the problems we have, and by Simon Sharp, called 5 Times Faster. It's a really nice book, which I'd highly recommend. Actually, it's both motivating and a bit scary, but also sort of super positive in what it's suggesting. So Simon says, still, our appreciation of the risks of climate change is limited by the way our academic institutions encourage each researcher to focus on their own narrow area of expertise. And that really resonated with me, and this kind of, the fact that we weren't talking with the scientists, and I was very fortunate then to be able to help set up this thing in Cambridge called the Institute of Computing for Climate Science. So lots of people are aware of this, that we need to have more interdisciplinary interaction and between lots of disciplines as well, because there's so much that goes into climate science. So we set this thing up to basically maximize the effectiveness of climate science research via all of these different disciplines and sub-disciplines. Climate modeling is a heavily computational field. It always has been. Climate scientists write code day to day, probably at least as much as I write code day to day. It's a core part of their jobs. Advancements in maths, advancements in data science, machine learning, all of these can be brought to help with climate modeling. And we were very grateful to receive support from Schmidt Sciences, who have been funding lots of university research in this area. They have something called the Virtual Earth System Research Institute, where they funded 6 large projects. These are all multinational projects as well, lots of groups working together on various different aspects of the Earth system, trying to advance the state of our understanding and the state of our modeling and the ability to sort of forecast and predict more accurately. So there's lots of really interesting bits of work captured in here, and we're sort of a bit of a hub between all of those projects, and we have a team of research software engineers who work day to day with the scientists in these teams, helping them with their programming, helping them build new models, write data analysis pipelines, have things that are reproducible, have things that are high performance, have things that are well described, that are more easy to share and plug together amongst all the different models. So with the Institute, I kind of see that there's sort of like multiple streams of work going on whose impact happens at different speeds. We've got the sort of immediate impact things with our research software engineers who are doing amazing work. Out of this, we find sort of common problems in which we try and then build sort of solutions like libraries or tools that can help across the different groups in the next couple of years. And then there's the sort of more like open research questions then where I sort of float between these layers, trying to, okay, understand what are the problems, and then think, well, what are the kind of programming language tools and systems that we could build that would help in the next sort of 5, 10 years and so on. So we'll come back now to our global circulation models, GCMs, also called global climate models, and as I said, at the core is the fluid dynamics. That's a big part of the core simulation. And of course, over time, we've been able to increase the resolution of those models. So these are from the IPCC reports. This was the first assessment exercise where the grid squares were roughly 500 by 500 kilometers. And in actually a different graphic here, but it's the same kind of information. This is from AR6, so the most recent assessment report. You've got 50 models in CMIP, that's the coupled model intercomparison project. So 50 different models, and you can see the resolution in the atmosphere is sort of going up towards about 25 by 25, 50 by 50, and in the ocean, about 25 by 25. So they're sort of, you get, in theory, you get better predictive performance if you increase the resolution, and that's what people have been trying to do. And in some shorter runs, people can get down to sort of 5 or 1 kilometers now. So there's that kind of scaling up. But when you're doing your fluid dynamic simulations and you've got these sort of grid boxes, there's a bunch of stuff that happens below that kind of minimum resolution, right? If I've got 5 kilometers by 5 kilometers, there's still a load of stuff happening in that has a massive impact on the weather and then the climate. So ocean eddies and clouds. Clouds are a classic one. They transport momentum, they transport energy, they transport water in the atmosphere, and they are typically much smaller than the minimum resolution of our fluid dynamics. So a load of work goes into then writing these what are called subgrid models or parameterizations that recapture the physics going on in those small squares. But often that's a source of error, source of uncertainty, there's lots of approximation, and actually they can still be really expensive, and there might be hundreds of these in a climate model. So there's a lot of work now in trying to optimize those as we sort of add in more and more processes. Doing atmospheric chemistry is really, really expensive, and there's still just so much work to do on the land surface modeling as well, and there's just there's not as much data about that kind of thing as well. So as pieces of software, as I said, these are really interesting beasts. These are graphics that are from this wonderful paper by Naughton and Easterbrook. They looked about 10 years ago now at the software architecture of climate models. Have this really nice kind of analysis of the architecture of these things, and you can see they're sort of you can break them up into components. So CESM is this open source community Earth system model that's developed primarily by National Center for Atmospheric Research in the States. Has a sort of big atmospheric component, ocean, land, sea ice, and then this coupler that sort of integrates things, and you've got some other subcomponents in here. So you sort of see how these things break down. But in each of these, you've got a lot of fluid dynamics. So where are people going in climate science? Well, there's been this sort of long talked about thing that, okay, we want to get better prediction, we want to understand what the kind of tipping points are, what the extremes are, and so we need to have more and more processes and higher resolution, sort of climb this ladder to get to this sort of golden egg of sort of very high resolution, everything we can think of in terms of the processes, do data assimilation where we take in observational data, work at multiple scales, and be able to do uncertainty and risk assessment. Now, of course, this involves scaling up computation. We have to sort of scale up the amount of computation that gets done. But I think this also breaks down into some other scaling challenges. One is scaling up collaborations. These models, the large ones, really involve huge amounts of expertise. You've got lots of different kinds of scientists with expertise in oceans and atmosphere, and they have to all come together and talk and build these things together. So that needs to be scaled up. And part of that is scaling up communication, and that's both communication between people and communication with the computer, right? That's programming languages. And programming languages are our medium for communicating with the computer, but they can also be a medium for communicating between ourselves. So, okay, we know that there's a challenge as we scale up the resolution. Okay, we have to do more and more and more work. If we just double the horizontal resolution, okay, then we need 4 times the number of grid points. Then we need to do, if we do that, we need to do 2 times the number of time steps, because we need to run things faster, so we're capturing the propagation of waves properly. So, okay, that's 8 times more computation just in the horizontal, and once you get the vertical in, okay, that's even more. So, you know, it's scaling up the resolution is difficult, and there's lots of really you know, it's a big data parallel programming challenge, basically. And then you want to be able to try, basically what people do is something called ensemble runs, where they do lots and lots of runs of a climate model, but with lots of parameters tweaked, and like, oh, well, you know, just to kind of, because we know there's uncertainty in it, so it sort of gives us a nice spread of understanding of the kind of, the envelope of what might happen. So, okay, we're probably very familiar with graphs like this, and the climate scientists are well aware of this as well. This kind of slow down in scaling, which is more like the sort of Moore's law scaling, but it's more like Dennard scaling is sort of slowed down. So we've got this sort of single-threaded performance is tailing off. So there's a lot of thinking about how do we exploit the parallel architecture more readily? How do we use GPUs more effectively? I mean, the climate models have always heavily relied on parallel programming, but lots of MPI and OpenMP, and GPU is finally becoming sort of more and more used and exploiting that. But even then, there's a lot of work on actually trying to replace the approximations with something that's higher performance. So there's a lot of really interesting work, which actually seems quite effective, about replacing these subgrid models with something that's data-driven using machine learning techniques instead. So rather than doing some kind of approximate physical model there, you train a neural network on a very high-resolution simulation, or you train it on observational data, or on both, and you replace the previous sort of handwritten model in there with your neural net. And in some places, that has been very effective. You get something that has at least as good predictive power, and in some cases, actually faster to compute with the net than it is to do the original model. Of course, that raises up questions about the generalizability and the explainability. You know, it's trained on some data. How well will it generalize? Can it capture things that we haven't thought of? And how do we understand it? And then there's sort of a bunch of software engineering challenges, which we spend lots of time working on, dealing with building these things and then coupling them back into big Fortran pieces of code. So I think another part of this then, as I said, is about scaling the communication, and that comes down to this programming languages kind of challenge. I think we're all kind of familiar with this idea of there being sort of, in programming, like the inherent complexity of what you're doing, and then the accidental complexity. So I think, you know, I don't think that we should just stick with the current languages that we have in science. I think at the moment, the languages, they don't help us support, they're sort of inadequately supporting the inherent complexity of the models, and then they're making it too easy to introduce this accidental complexity as well. And that's the lesson that I learned writing that C code. You know, the thing that I was doing was inherently complex, and then when I was doing this MPI 2D decomposition, I was just making it more and more horribly complex with my 2D thing, and it was just too easy to then, and then all of those complexities were mixed together and difficult to separate out. So both of these hinder scientific progress. I think only one of these is truly necessary. Okay, sometimes a bit of accidental complexity is going to sneak in, But in the design of DSLs and languages, I think we need to be moving towards supporting this as much as possible and squashing out this one as much as possible. Now, as I think, sure many of you have thought of, and as I was talking about with Hypnos, one of the things was like avoiding the overcommitment to details. So instead, I wanted to leverage the comonadic pattern to let me hide the details and not just sort of make something really specialized to column major order in Fortran arrays with an MPI decomposition. No, let's have something that's more abstract that we can then overload. And this is something that scientists are becoming increasingly keen on and building their own tools for, in collaboration with computer scientists as well. So there's something called grid tools for Python, which is a kind of DSL for writing stencils that tries to give you just this kind of more abstract representation that you can then compile down to different targets. So they've got, they turn the indexing into just these offset vectors that you apply to things. And then they use the Python contextual operation with to do sort of with computation parallel and abstract some of this stuff. So, I'm sort of like greatly encouraged by the fact that these ideas are being used and people are thinking about them and people are really sort of starting to take this kind of thing seriously. And I'm also sort of itching to get a bit more involved because it's like, hey, this is my bag, right? So should try and get involved with these projects and help out. Another thing that's good about trying to avoid overcommitment to details by sort of leveraging overloading is that you can reinterpret bits of code as well. And this is something that people are increasingly doing. So, for example, Julia is becoming really popular in scientific computing, and actually there's this whole project at MIT and Caltech called the Klima Project, where they're implementing a new global climate model from scratch using Julia, which is really exciting because it's a sort of new language that's got some cool ideas in it. And a thing that you can do in Julia is do dynamic multiple dispatch, which lets you do lots of overloading. So you can write a bit of code using just plus and multiply and things like that. Maybe like you would do using a Haskell num type class. But then you can redefine plus for some different numeric types. So in this bit of code, we're doing the dual number representation, and we're writing down what is plus and divide for, and you do all the other operations for this dual number representation. And so you can take a bit of numerical code and then just say, oh, the inputs are dual numbers, and run it again, and it gives you the automatic differentiation using the forward technique. So it gives you the gradient for that function, and so then you can use that in a machine learning context as part of your loss function to then train your neural net. And you just had to write your normal piece of code and then just overload it to the dual number representation. So I think, again, that's really about leveraging being not overcommitted to the details. And it's sort of, again, really encouraging to see that languages like Julia have sort of hit a sweet spot that people are starting to pay attention and say, oh, this is good. I can write code that I can retarget in different ways and recompile or reinterpret and have this one bit of code that I can do automatic differentiation on, and I don't have to write anything special for it. So this brings me on to the very last cycle, which I'm not going to spend as much time on, but this is the kind of the next stage, as I spent all this time working and talking to climate modelers and then really thinking about how do we evolve the languages? What's the sort of the revolution here that's going to help in the future? And I'm not necessarily thinking I'm going to make that language that everyone uses. It's difficult, that requires a lot of time, but at least maybe we can develop something that sort of by infection can sort of infect something else where there is enough engineering effort and momentum, like Julia or something else in the future, and these ideas can be picked up. And I think, the history of programming languages, you can see that lots of neat ideas get developed in academia, and eventually they kind of, lots of them do make their way into something eventually. And you look at the things that are in Rust, the things that have gone into newer versions of Python and Java and C++ and so on, the ideas make their way in eventually. So, okay, how do we solve this overcommitment problem? Perhaps we go back to the comonadic combinators as well. So I'm sort of thinking about that again. Can we go back to structuring something around these combinators? I think something that's really kind of unexplored there that we sort of thought about but didn't do was really working with lots of different kinds of spatial data structures and connecting those together with the arrays. So you can imagine having something like a quad tree representation, or like a tree of arrays, and this is also a comonad, so you sort of have this way of having different resolutions all within the same grid, and if this, the idea is you coarsen when things are kind of a bit less busy, a bit quiet, then you don't need to do as much computation there, so use this quad tree representation. I think that an idea that I'm sort of starting to explore again is whether you can write a single kernel, a single stencil computation on one grid, and then have this, what's called a comonad morphism, that maps from one representation to the other. So then you can turn this dA to B, maybe this is like a simple grid A to B, into a spatial grid, SA to B, and then lift this to work on the entire spatial grid. So you only have to sort of write something once, and then the detail comes in this comonad morphism that handles that mapping. So you can kind of give your stencil computation on the flat view and then have the spatial view mapped to it. So again, back to this hiding representation, but now use the comonad morphism in here. So perhaps there's a bunch of different categorical abstractions we can use. So we've got the comonad morphisms to go between grid representations. And actually you can see people are already starting to build models which have lots of grid representations in them. So this really neat little intermediate complexity model called Speedy Weather, which is written in Julia. And one of the things that it does is let you really work with different grids and different kinds of grid layouts and different resolutions, all within a single model. So I think this would be an interesting test bed to kind of try out some of these ideas. And there's other operations you need as well, like to do reductions and filtering, but I think those can all be captured by some other kind of distributive laws with a monad. Another problem I've sort of alluded to is this semantic gap, this sort of like problem in communication, and you can see this a lot where you have papers that describe this really abstract model with a load of PDEs. There's maybe some solution numerical analysis that's sketched somewhere, and then you've got the code. And connecting these things back together is really difficult. Often the code is not really clear which parts are related to the original equations and vice versa. Looking at the equations, it's hard to connect them back to the paper. There's sort of a semantic gap that you have here, and that makes it difficult to make progress. So, just to land on this again, sorry. So, one of the difficulties with that is that when you're trying to use someone else's model, and maybe you're trying to take one of these subgrid models and you want to move it into a different model okay, I've got a really good model of convection in this over here, and I want to put it into this other model and see if it also performs well over there. And one of the problems we've seen, we do a bunch of projects like that, and an issue that I've seen is that there's just not enough information in the code. You sort of get things that look like this, and you say, okay, great, this convection model has some arrays of floats as inputs. Okay, what do those exactly mean? And okay, typically they have some comments, but then those comments can be a bit partial. So what I really want is to have a language where you can put together lots of bits of information within the type system. So say, this y_in thing, it's an array of floats in dimension x, it has unit meters, but particularly that kind of meters is an arc length quantity because you're measuring a distance of a column of air from the equator. So it's really a length across a sphere. And okay, if that's the case, and we have a refinement type that says that its value has to be less than 10 to the 7, because that's the half of the circumference of Earth, pretty much. And okay, this is a temperature thing, and it's absolute temperature in Kelvin, so it needs to be greater than 0. And here's static energy, and okay, it has this unit as well. And these are like semantic tags that then you can link to documents as well. So I'm sort of getting, okay, that's a bit array from arrays, as I was talking about, but trying to build languages where you can get a lot more information about your actual domain into the code via type system design. So to kind of then conclude with a grab bag of ideas then, so what could this language look like? What are the things that I think are useful to consider for such a language? that could actually help scientists. Okay, it has to be sort of science-oriented, and we have to look at the actual kind of things that people are doing there. I think a big part of that is about describing the domain. Of course, it's got to work with arrays, and you can see all of the huge amounts of work that go into sort of array libraries in different languages. And I think one of the reasons that Fortran has remained popular, it has a lot of sort of sociological inertia behind it, but arrays are first class in Fortran. You can do A plus B on two arrays, and it does the pointwise addition of those arrays, and it parallelizes it for you automatically. That's great. That's what you do in MATLAB as well, and you can do it in Julia. There's lots of really nice libraries that people are building on top of Python, NumPy, Xarray, XGCM, that embed lots more of these kind of array patterns with lots of information in them as well. So it's got to have things like that. Interactivity is increasingly important. REPLs, we know, are really cool, and people use those as well. Notebooks are very popular in science, and I could say a lot about notebooks. They're kind of useful for interactivity, but then they sort of push you into a corner where then you end up with code that's not very modular or reproducible, but that's another rant. Overloading, I think, is really important, again, for that retargeting, doing things like AD and symbolic execution, and core to that is, again, this low commitment to the implementation details. We have a project, which I'm not going to talk about, called the Fluid Language. That's in our institute, Roli Pereira, and that's all about having explainable and transparent visualizations and code. Go and have a look at that online. There's some talks on YouTube. Search for Fluid Language Pereira. So having sort of runtimes that then give you access to understand the provenance of the calculations and let you kind of really interrogate how the evidence was generated. Of course, it's got to be fast, though, right? And actually, I haven't really had any graphs today. Sorry that FProPer. I probably should have had some benchmarks and things like that. But people use Fortran because they can write fast code. And okay, in the future, anything we build, it's got to be high performance. And Julia is getting really, really good performance. We want heterogeneous compilation, of course. We want to be able to target all the new architectures and systems. And my favorite topic as well, lightweight verification, bringing some of these specification systems in so that people can just be more productive because they've got something that is checking things for them, using types, and that helps them communicate better between them. So one of these big problems is this semantic gap. We spend huge amounts of time discussing, what does this variable mean, and what's its units, and is it an absolute value, or is it a tendency? Is it, what's its resolution? Having these things specified and checked would be excellent. And yeah, program synthesis. Yeah, let's have things written for us when the computer can do it. Okay, so I'm going to end with with an advert. If any of this sounds interesting and you'd like to come and work with me, I have a postdoc available at the moment for just under 3 years at Kent. It could be on anything really in this space. Could be about static analysis, could be about verifying critical libraries used by scientists, could be about these novel languages or extending existing languages. If you're in that situation where you're sort of looking for a postdoc or you know someone, then you've got until Monday. So I made the advert finish as late as I could, so it's just after ICFP. And of course, developing new tools. Okay, so I'm going to end with another quote from Simon Sharp, which is a sort of a challenge for me and for everyone, to think about this general problem that we have. We know the situation is a bit difficult, but Simon has this great quote: any actor should understand their points of leverage. We each have to understand the opportunities presented by our place in the system and do our best to exploit them. So whether that's at a personal level or a professional level or in your communities, whatever you're involved in, there's some way that you can have the most leverage. And so have a think about what that is and try and use that leverage. So thank you very much for listening, and happy to take questions. Thank you. Hi.
Really interesting talk. I really enjoyed, and I'm really excited whenever you apply here to some applications. So regarding the pattern matching for indexes question, I assume
Yeah, that's a great question. So, you know, what about sparse representations where we have some sort of like indirection kind of arrays in the middle? So, I think our philosophy here is that you have the sparse, you can do a sparse matrix comonad, but then what you expose is a kind of dense view on that. So you still index it in the sort of the dense way, but then underneath that's mapped to the sparse via the indirection. So rather than exposing the sparseness, that's like an implementation detail that you hide inside the comonad.
So in that case, how would you interact with the libraries that are written with sparse representations?
So I think in something like Hypnos, you are really restricting yourself to certain patterns. So it is a bit like you can't do everything. It's sort of like, here's the things that you can do, and here's the things you can do fast and predictably. So it is necessarily restrictive. So there are things that you wouldn't expose, so it would reduce your expressivity, but gaining the kind of performance. And then you hide, you write the underlying implementation to deal with those libraries. So if you wanted to capture everything, then that sounds like a harder but interesting problem that I don't know the solution to.
Yeah, that's interesting. And the second question that I have is regarding like the MPI stuff. So in the slides that you have presented, I suppose it's a very sequential style of writing programs. What happens when you have parallelism, like message passing and stuff? How would you model that with comonads and that kind of stuff?
So you can hide all that stuff inside the comonad. So the comonad can do the domain decomposition. It can split things up. So in Hypnos, you statically know the size of your kernel, so you know the size of your halos, and then you do some calculation of how much you're going to split it up, and you know the halo sizes, and then it's all hidden. So in terms of an MPI or a GPU implementation or something, that's sort of all in this, I've chosen this particular comonad, and it does that parallelization inside.
Okay, thanks so much.
Thanks. Great. Ooh.
The kind of like scale of energy that we use is like orders of magnitude of the whole country, right?
Yeah.
Globally.
Yeah. Yeah, this is a really great question about, energy efficiency. I haven't done any work myself about it. I suppose at a very coarse grain level, you could say, higher performance means less energy, using less cycles, less memory. So there's a relationship there, which has some subtleties to it as well, because it's not a one-to-one mapping, I don't think. There are people who are thinking about this. There's a group at Glasgow, the LOCOS, LOCOS group, who are thinking about this kind of thing. And there is sort of various sort of movements around sort of green HPC and green algorithms. So it's something that people in this space do think about, and there's increasing sort of, okay, what we could do with is more monitoring tools on HPC and clusters to understand how much energy did that job use, and estimate in the future how much energy something uses, and can we schedule it at certain times of day, like during the day in the southern hemisphere when there's loads of sun, or in the summer, or things like that. I'm not doing any work on that specifically, but I think it's really important, and there are people out there doing that. Suddenly got louder.
Any other questions? Thank you for the talk. It's very good. This question I'm wondering about is, well, I think you put a lot of emphasis on sort of abstracting things away and abstracting the raw level detail. So what tends to happen with that is you limit the optimization potential that's available, because it's a weak abstraction, like you don't get to see the generated code often. And I think the comonads is like a really nice abstraction for this sort of thing. But like, what is your position on like whether there exist abstractions where you can actually like the compiler can do the entire work and no one actually has to see the low level code? Like, do you have like positions of like how should expert programmer be able to optimize these things further?
Yeah, this is an important question. It's sort of it's a long-running question, isn't it? And that went back to my arguments with my roommate I want to write the C code because I can make it way faster. I suppose there's a bit of an axis, isn't there? Because it's about this almost like productivity and performance. You could see as kind of two axes. If I want to write some code really quickly and get 95% of the performance I could, but it took me a day to write it rather than a month, then that might be a good thing. And I can write a model. I'm a scientist. I can write a model. I can try out loads of things. I can try out lots of different model configurations and try out lots of ideas. And okay, it's not the fastest, but I could explore the science more easily. I was more productive. So I think with Hypnos, that was our kind of trade-off in the space. We trade off some of that squeezing out every drop of performance for I can very easily write code and understand its performance. But of course, there is a time and a place for that squeezing things out. And if you go to sort of the high end of climate modeling, where we want to run as high a resolution model as possible, we want to simulate 200 years, and we want to try 200 different parameters or more, like tweaks, then okay, that maybe is going to take a year of computation. So being able to save a few days and a few megatons of CO2 is maybe really important. And I don't really have a good answer for you in the kind of things that I've been doing. I will say that something I've observed, which is interesting in Julia, is that it lets you inspect the compiled code at different stages. So you can use macros to sort of reveal what's the intermediate representations, what's the underlying LLVM. So what people do is they look at that and they learn really how things are behaving in the compiler, and then they tweak their code to squeeze that out. So they're not down doing the LLVM themselves, but they learn how to push things in the right direction to get the highest performance code. So in a sense, that's having a mechanism for inspecting all of those steps and understanding them. And so I think that was one of the things that we thought about earlier with Hypnos. Like a lot of the automatic approaches, or even these abstract approaches, a problem they can have is that they're just completely opaque. So if it doesn't do what you want it to do, you're just left saying, I don't know why that wasn't as fast. So I think having more explainability in compilers and these kind of things is really important. Say, well, I did this for this reason, this for this reason, and I couldn't do this for this reason. And therefore you can have things that you can tweak. And I think you'd probably do eventually need to expose some details. And okay, you could go in and tweak the comonad definitions yourself or something like that. But I think, I suppose, surfacing that to the user is really important, and that's what's happened in Julia, and I think that's one of the things that's also making it really popular. People are looking at the LLVM code it generates, or like then step up and go, okay, now I want to be a bit faster, so I need to specialize this thing, and okay, now it's done it. So there's a lot to be gained in those scenarios from explaining what's happening and exposing some of that representation underneath, eventually. And then that's that's in a different scenario when you're willing to lose the productivity because you want the performance.
Any quick final question? Maybe two quick, super quick questions.
I'm just curious about something confusing me. That is, how is it different from one specific language and then organized by some optimization process with MLI or something like that? How is it really different from this approach, from the PR for this component approach? Like approximation of any specific language, for example, specify more specific terms or anything. The optimization process just apply those optimization or rewrite custom on for that library, for instance.
Mm-hmm.
How is it different from the PR approach computations?
So how is the approach of Hypnos different to that kind of thing, or? I'm not sure I fully understand the question. So you like a comparison between?
Type system approach. It seems from a type system approach and try to expose the concept to the users with some specification for checking.
Yeah.
And how is it different from directly writing a domain-specific language for the kernels, and then to let all the compilers recognize to the optimization on that domain-specific language?
Right. Yeah. So I mean, perhaps they're not kind of mutually exclusive. So I think a nice thing about type systems is that they're an intrinsic mechanism that's about a kind of dialogue between you and the language. It's sort of telling you the things you can and can't do, and it's encoding lots of information. And with Hypnos, what we wanted to do is really get as much information available to the compiler. And a lot of compilers, what happens is you take a language, you throw away a bunch of information, and then you do static analysis to try and recover that information. And maybe it does or doesn't get that information back. So we're like, let's cut that out. Let's capture as much information statically as possible so that the static analysis is very easy. And I think part of the kind of program of types, or at least the way I think about it, is sort of exposing that information to the user and having it be like an intrinsic part of the thought process, rather than, well, you write some code and then some analysis happens on it later and then maybe some good stuff happens. So I think having DSLs to write down some kernels versus like a typed approach, those things aren't mutually exclusive. Hypnos was trying to put those two things together and sort of use the types to let the programmer communicate to the language and to the compiler. This is what I'm doing. This is the shape of this thing. These are the boundaries. This is the dimensionality. And then go and use that information to compile. So, and then having the type checker kind of force you to do things in the right way and say, well, your stencil looks one to the left, so you need to have a boundary one to the left as well, rather than letting something fail later on. And I spent a week letting things fail later on and couldn't understand it. So it's about the understandability, I suppose, with the types.
Thank you very much. I'm afraid we have to take it off.
Well, yeah.
Thank you very much again.
Thank you very much.